is something, a little bit of digression here, which is, I've called it the power of expression, right? All of you know that same thing can be said in many different ways. Some are better than the others, right? And we know the power of a quotation, right? We use quotations to convey certain points. We also, poems. Some things we can say it in ordinary words. Some things can be said in the form of a poem. And so the way you express something carries weight. And there are different ways in which one can express, right? So now, power of expression in the field of language, of course, we know. But what about in this area, in our area? All right. So let me give it to you. So suppose I have a circuit. I'm not showing you the circuit right now. Okay. I have a circuit. I've applied a voltage Vs, and there's a current Is flowing. Right. And suppose I solve this particular circuit, and I get this expression. Okay. I get this expression. Is, R2 plus R3 plus R4, all these terms are there. There are, as you can imagine, I have 4 resistors in my circuit, right? I can see here R1, R2, R3, R4, all these resistors are there. And the current depends on the voltage, and I have this expression. So I can express it like this. Okay? Can you tell anything about the circuit from this? Linear circuit, yes. Anything else? What is the structure of the circuit? We know 4 resistors are there. Can you tell anything? Now, let me give you another expression. Same thing is being said, another expression. Look at the second expression. What does the second expression tell you? What do I have in the circuit? Huh? Series. Right. So can you sketch the circuit now with this information? Will it look like this? Right? So I have two expressions here. Both will give you the same answer. R1, R2, R3, R4, you substitute here, you'll get the same current. You substitute here, you get the same current. Right? As far as getting the value, both are same.
There can be more than one.
There can be more. Exactly. What I'm pointing out, there's more than one way of expressing something. What is the advantage of this one with respect to this? It's showing you the entire structure of the circuit in the answer itself. It's giving you more insight into the circuit here. It tells you, looking at this expression, I can't tell whether R3 is in series with R4 or R2 is in parallel with this. Right? So what I'm raising is an important issue of when in semiconductor also we derive expressions. You can write it in one way and you can write it in another way. And the two ways of writing the expression are not equivalent. Right? So let's come to semiconductors. VBI. We've been writing like this. KT by Q, ln ND by ND into NA by NI square. Right? So, and we'll get the value of VBI. We've just substituted ND, NA, and we've gotten the built-in voltage here. But are there other ways of writing this built-in voltage which will give me more insight into what really built-in voltage is? Now, suppose I write it like this. Let's see. Let me rearrange like this. Same equation, minus VBI by KT by Q, ln NI square over NA by ND. No, it's not providing any further insight. As compared to this, what am I talking about? This equation, if you have a log, what is it pointing out to you? This? Is it pointing out this? Ni square over Na is Nd exponent minus Vbi by Kt by Q. It's telling you what the origin of Vbi is. Why do I have a built-in voltage here? It's telling you that I have Nd as a electron density here. The electron density on the other side is Ni square over Na, and the two are Nd exponent minus Vbi by Kt by Q is equal to Ni square over Na. I have a lot of electrons here. By the time they overcome the built-in voltage, the electron density becomes small Ni square over Na. That's what this particular expression is telling you. In this particular expression, you don't see that. It's all jumbled up. While in this expression, you see it clearly. Ni square over Na, the electrons that reach the other side of the p-n junction, is equal to the electrons on the n side multiplied by how the barrier is overcome. What the effect of the barrier is exponential, VBI by KT by Q. Okay, so that's what this particular expression is telling you. Both will give you the same VBI, but this gives you what VBI really does, what a barrier really does. It reduces the electron density. How does it reduce Ni square or Na and Nd on this side? Let me go forward and give you one more example here. Depletion width in a p-n junction. We just saw, right? So let me write depletion width here. We wrote this. Depletion width. So I have VBI minus V, Q by 2ES, ND, NA, ND plus NA, W square. We'll get the depletion width, right? But suppose now, same expression, I write it like this. Look at this one. Looks more complicated than this, but actually is easier than this. Looks more complicated, but is easier than this. Because it's based on an insight. Half Q by S ND W by 1 plus ND by NA into W. There's a different expression. The terms are arranged differently. Same value you will get. What is this based on? Well, it's based on this picture of depletion region that one carries. What is VBI minus V? Is the net voltage drop. What is it equal to? Half Emax, right? Emax is what? The maximum into W. So it's telling you how to estimate VBI. VBI minus V is half Emax, maximum E, multiplied by W. So this is Emax, and this is W. What is Emax equal to? Emax, now, how do we calculate Emax? The slope of this line is what? Q by ES into ND. That's the slope. Poisson equation tells you the slope of field is Q by ES ND. So the slope, Q by ES ND, multiplied by what will give you Emax? Xn. So this term is what? Xn. And how do you write Xn? We just saw W divided by 1 plus ND by NA. So it's telling you, again, another expression for VBI minus V, but it's telling you how this expression has been derived. Right? All the derivation is there inside this particular expression. The whole derivation is there contained in how you arrange the terms. You can see it there. While here, the terms are all jumbled up. Right? Both will give you the same answer, but this one provides you with a method by which the VBI has been calculated. So what I'm raising is, in general, the expressions in engineering and elsewhere, we keep on deriving expressions, but how the terms of the expressions are arranged can give you a lot of insight and help you in appreciating some things better.